Hi everyone, my name is Daniela Figueroa. I am an electromechanical engineering and systems technology major here at Cal Poly Pomona, and today I'm going to explain to you my senior project. I have been working on a modernized atmospheric water generator, and in the next 15 minutes I will be presenting to you what is an atmospheric water generator, why atmospheric water generation is important, how atmospheric water generators work, my specific atmospheric water generator design, and what makes my atmospheric water generator design unique. So let's dive in. What is an atmospheric water generator? So atmospheric water generation is a semi-new technology that people came out with in the 70s and patented in the 90s. And this device uses electrical and mechanical components to generate water from the ambient air. We are able to do that because our ambient air is filled with humidity, and that is water vapor. And this type of technology has the potential to provide usable, drinkable water during storms, during shortages, during droughts, during any type of contamination event. And yeah, there's a lot of potential for this type of technology. So why atmospheric water generators? Well, right now, at any given moment in time, our Earth's atmosphere alone contains 37.5 million billion gallons of water, which only amounts to be less than 1% of the amount of water that the globe holds. And all of that water vapor in the atmosphere also plays a part in our greenhouse gas effect. Water vapor is the third most important greenhouse gas, right next to carbon dioxide, right next to methane. It traps heat. And so, as you may know, with more heat being trapped, the surface temperature rises. And with the surface temperature rising, more ice is melting, our water temperature is rising, more water is evaporating. So there is more water that's being put into our atmosphere and circulated into our atmosphere more than there ever has been in the history of humanity. And all of that water vapor has an effect on humanity. And we actually have been able to witness it with the weather storms that we've seen in recent years. Many of you may have noticed that the weather storms have increasingly gotten more severe, and there's more of them. Like hurricanes are more frequent in our nation than they used to be. They're more severe. Rainfall is pouring harder, even though it may not be as frequent in our state, but it's coming down harder and for shorter periods of time. And then also flooding is another thing that we're going to have to be more aware of, as there is more water vapor in the atmosphere that we're not really collecting to drink yet. So yeah, water vapor increases weather storms around the world, and too much water vapor in the atmosphere may not be good for us. And which is really funny because we are actually dealing with a water scarcity problem around the world. About 1.1 billion people lack access to water. 1.1 billion. And many of you may not know, but all the water that we are able to drink comes from fresh water sources, and those fresh water sources make up 3% of the water that this planet holds. And out of that 3%, 2/3 of it is our glaciers and our ice that is slowly melting. And a lot of that fresh water is also contaminated. So along with people not being able to drink water, the water that we do have to drink is filled with contaminants. And in the next slide, I am going to show you how real that is. So I was able to get on this website that I linked on the bottom called ewg.org/tapwater if you're interested. and it shows you how many contaminants your tap water has in your city. And I live in the city of Downey. Right now, well, not even right now, this is for 2017. This was for a couple of years ago. There were about 20 total contaminants and 8 of them exceeding health guidelines. And out of those 8 on the right, you can see them. Out of those 8, 6 of them have the potential effect of causing cancer. So that's a little scary and a little worrisome because of how important water is to our bodies and to our overall well-being. That worries me, and also the fact that we are actually paying for all of this. And if we have the option to pay for something that is mineralizing our body and helping our body rather than paying for something that could potentially give us cancer, I think that's an option that many people would appreciate to have. And that's what I want to do with this design, is to provide that option. So how do atmospheric water generators even work? You may be asking. They are similar to dehumidifiers, and in the sense that they simulate a dew point temperature within a mechanism to condense water from the air. So what that means is the dew point temperature is a temperature that a molecule of water vapor needs to reach to condense to liquid. So I can show you an example. Picture some hot, humid air coming into this Google diagram of an atmospheric water generator. So hot, humid air at a dry bulb temp of 75 degrees Fahrenheit and with a 78% humidity. The dew point in this case would be 67 degrees Fahrenheit. Therefore, we would need to simulate a 67-degree environment within the evaporating and the condensing coils, which would be these coils right here. So how this works is we have some refrigerant that's being compressed by this condenser into vapor, which gets really, really cold, and these coils get really, really cold. And so that's how we simulate that dew point. And so that's how we can get that liquid condensate. And after that refrigerant gets these guys really, really cold, it goes back down through a filter dryer and gets recycled back and through the cycle. And we are able to use that refrigerant for a while. So that's how they pretty much work. And then we are able to capture that water and filter it out and use it, remineralize it and drink it and use it for any other needs that we might have. So moving on to my specific atmospheric water generator design. On the side here, I show just a couple pictures that I've acquired over the time that I've been designing this. To dive deep, I am going to start off with the components that are making up this mechanism. This design is utilizing a combination of a refrigerant and a hydrophilic surface-based system for generating water. And this system consists of the use of metal organic frameworks and a uniquely designed heat exchanger, along with methods of water purification. Some components that I have pictured here are all the little components that come in with making this design. Them being air filters. This is a MAW filter to filter out the air. This is a fan to pull in the air. Compressor and a thermal expansion valve, along with the filter dryer. These are all for the vapor compression cycle. Then we have the air pump, the water pump to pump the water and to add oxygen to the water. And then we have a refrigerant here, which is going to be the liquid we're going to be using to compress and condense and evaporate. And then we have our reverse osmosis filtration system. So I wanted to share a little bit of knowledge about metal organic frameworks because they're fairly new. And they're hybrid materials that are very porous. So they have the capability to do a lot of absorbing of different types of gases. And they are also utilized now in separation, purification, and gas storage. And in this specific application, I will be using multiple MOFs for air purification and for water absorption and condensation into liquid. The first MOF I'm going to talk to you about is the air filter MOF that I'm going to be using at the beginning of this cycle. It's going to be right in front of the air vents, waiting for the air to be blown in and to collect any particulate matter, any excess carbon, hopefully. And so this MOF is the CU-BTC/PAN film MOF, and that stands for copper 135 benzoic acid, the CU-BTC part, and that is synthesized using a hydrothermal method. And once that's synthesized, we can add it to the PAN, which stands for polyacrylene nitrate. And once the molecules like mix together, we are able then to synthesize it using the method called electrostatic spinning. And once this is done, once this method is done, it is turned into like a fabricy film. And on the right, I show these pictures of really zoomed in photos of this like nanoporous film. And so the thing about this type of material is that it's actually been proven to already be 8 times better than the regular semi-crystalline organic polymer resin films that are used in filters. And so with that, this caught my eye because I wanted to use a really good filter and also utilize MOFs. And this filter happens to be way better. And the next MOF I will be utilizing is this MOF called MOF 303. And it is a aluminum-based MOF. And it is special because it can capture, or it can capture water vapor from the atmosphere and then release the liquid water vapor, or the liquid water, when exposed to a warmer temperature. And on the left here, I show a picture of how that may look like. And so we have in side A cool day where the sun's not shining on the MOF and it's able to absorb all the water molecules, and then a hotter time when the sun is shining directly on the MOF and the MOF is absorbing this heat and it's able to release this water like a sponge, like if you were squeezing a wet sponge. So moving on to the next slide, I am going to be explaining to you the water purification process. We are going to be using 4 methods of water purification, one of them being a reverse osmosis filtration system, which basically just moves water through membranes that are going to be picking up on pollutants more using pressure and a pump, and a sediment filter to pick up any sediment from the water, and a UV light sanitization system that is going to be shining light to sanitize the water that's going to be coming through, and a remineralization process that will be re-adding minerals back to the water to be healthy to drink. So next are the CAD drawings and block diagrams and schematics. So these are a couple of photos of my diagram. The dimensions of this mechanism are 6 feet by 4 feet by 2 feet. And here you can see we have a pump, we have the filters, we have the 2 tanks right here. This is a heat exchanger, and these are the components for it. This is the fan that's going to be blowing. And then we have the casing, and then the exploded glues right here. And this is how it looks like all put together. And the heat exchanger, to go into a little depth, is unique because it is an air-to-air heat exchanger, which means that it's going to be converging two airflows at once and transferring heat as well, or transferring energy as well. And so with our condensing center right here, or a cooling center right here, we are able to condense or simulate that dew point and then condense the water from the air. And right, this little thin line, this thin red line is supposed to be the moth. And this moth will be able to absorb the water vapor and then hopefully utilize the heat coming from the evaporator to then release the extra liquid condensate that the moth can create into the water tank. And this slide is showing the schematic diagram. This is basically how it would work. So all powered by 60 hertz, which is any regular outlet that you have in your home, air coming in through the evaporator, through passing the compression cycle, fan blowing it out, water being collected, and then water being pumped through filtration process and being able to be used. These next 3 pictures here are pictures of a PCB diagram and the circuits for each PCB. And I was able to acquire these through a company I found online who was doing something similar. And I am showing these just to, simulate that if I were to actually create this mechanism, this is like on the same road that I would be on if I were to make these PCBs. And so these PCBs basically control everything in the mechanism. So the pumps, the compressor, the sensors, all the communications. And yeah, up here we see the circuit diagram for the display. So in my mechanism, there's going to be a screen where it shows you like important information about how much water is being generated, or if you need to like replace something. And then, oh, this is the display. And then up the main is going to be for the motors and the pumps and the sensors and the compressor and all that. And this is just for everything to communicate with each other so we can generate some water and filter it. And so this slide is showing just some key calculations that I was able to obtain. I was able to obtain the theoretical condensate generated per day. In the summer, we could get approximately 52 gallons a day, and in the winter, it would be 26 gallons. Total heating load of 8 kilowatts, 8 kilowatt hour in the summer and 8 kilowatt hour in the winter, and total power needed of 465 kilowatt hour in the summer and 310 kilowatt hour in the winter. These are all theoretical, just mind you. Next slide is showing my theoretical budget and some future steps that I will be taking after this semester is done. And so the budget consists of all the components and also some air, just for in case, and it comes out to $2,622, which is a little less than $3,000 and about the same, about average amount of other water generators out in market right now. And for future, I will be doing more research on MOFs and how to incorporate them more efficiently in heat exchangers and vapor compression cycles to generate a higher liquid yield. These are my resources, and thank you for sticking it through with me, and I hope you are inspired in some way, shape, or form.